comet from another star is supposed to do one simple thing when it enters our solar system. It is supposed to follow a path you can predict with gravity, like a stone thrown past a lantern. It comes in, it swings around the sun, and it leaves again, never to return. Clean, cold, mathematical. And then in the tracking data for 3IATLAS, that clean path starts to look slightly wrong. Not wrong by thousands of kilometers, not wrong like a movie scene where an object swerves toward Earth. Wrong in the way that makes scientists sit up quietly and open a fresh notebook. The kind of wrong that appears as a steady drift between where the comet should be and where it actually is. The kind of wrong that says something is pushing on this object besides gravity. Something small, something persistent, something that from far away looks like the comet has changed course. And the moment you hear that change course, you can feel your brain reaching for the loudest explanations. Engines, steering, signals, secrets, anything dramatic enough to match the drama of the phrase. But here is the calmer truth that makes this story better, not duller in space. A comet can change course without ever deciding to do anything. It can change course the way a wet bar of soap can slide differently, depending on where the water jets out. It can change course because it is not a silent rock. It is an active body leaking gas-shedding dust and turning sunlight into tiny bursts of thrust. It can change course because comets are not just objects moving through space, they are objects venting into space. So tonight, instead of treating the phrase "no one can explain it" like a cliffhanger, we will treat it like an invitation. We will take that supposed mystery and turn it into a clear picture. What 3IATLAS is, what we actually observed, what it means when an orbit doesn't fit, how scientists detect a course change so small that it only shows up as a pattern in residuals, and why in most cases the explanation is not alien steering, but something far more elegant physics you can imagine happening on the surface of an icy body that has never seen our sun before. 3IATLAS is an interstellar comet. The 3I label matters. It means this is the third confirmed interstellar object ever discovered passing through our solar system, after the earlier visitors that made headlines for different reasons. And Atlas refers to the survey that discovered it, a wide-field system designed to spot moving objects against the fixed background of stars. When 3IATLAS was identified and its orbit was computed, one fact stood out immediately. The path was hyperbolic, meaning it is not bound to the sun. It is moving too fast to be captured. If you trace its orbit backward, it clearly comes from outside our solar system. If you trace it forward, it will leave and never loop back. That unbound nature is the first key to the story, because when an object is unbound, it is already on an escape route. It doesn't need to change course to leave, it is leaving by default. So any course change we talk about is not the comet suddenly deciding to escape. It is a subtle deviation from the gravity-only trajectory that astronomers would predict if the comet were a perfectly inert chunk of ice and dust. But 3IATLAS is not inert. As it fell inward toward the sun, sunlight began to heat its surface. In the cold of interstellar space, volatiles, frozen gases like carbon monoxide and carbon dioxide can sit stable for unimaginably long times. But near the sun, that stability ends. Ice subliments, gas escapes, dust is dragged outward. A coma forms the fuzzy atmosphere around the nucleus. Tails form shaped by sunlight and the solar wind, and in that outflow, a new force appears, a recoil force. When gas rushes out of a vent on one side of the comet is pushed slightly in the opposite direction, the same way a slowly leaking balloon can drift across a room. This is the core idea behind non-gravitational acceleration. It's a real term in comet science. It doesn't mean something supernatural. It means that in addition to gravity, there is measurable acceleration caused by things like outgassing. And comets in our own solar system do this all the time. Their orbits are routinely fitted with extra parameters that account for thrust from jets. It's normal enough that in many cases you only notice it if you're trying to predict the comet's future position with high precision. So why does it feel more mysterious here? Because 3IATLAS is new to us. It is foreign. It is fast. It is observed over a limited window. And because interstellar objects carry the extra emotional weight of being from somewhere else, every oddity feels amplified. A small orbital deviation that would be shrugged at for a familiar solar system comet can sound like a riddle when it happens to an interstellar one. Now let's make the course change concrete. When astronomers track a moving object, they measure its position on the sky again and again, night after night, hour after hour, against background stars. Those measurements are fed into orbit determination. At first, the orbit is uncertain. like a corridor of possible paths. But as data accumulates, the corridor narrows. If the object were governed purely by gravity, a well-fit orbit should predict later positions with residuals that look like random measurement noise. But if there is a small extra push, if the comet is being nudged by jets, the residuals stop looking random. They start to align. They start to drift in a preferred direction. And when that drift persists across many observations, the orbit fit improves dramatically when you include non-gravitational terms. That is the signature of a real physical course change. In other words, the course change is not a single moment. It is not a sharp turn. It is a gentle accumulation of tiny differences noticed by the quiet persistence of data. And the reason it can look unexplainable at first is that the pushing force depends on details we don't know immediately: where the active regions are on the nucleus, how the comet is rotating, which volatiles dominate at different distances from the Sun, how dust and gas couple, whether the activity ramps up smoothly or in bursts, and whether the strongest jets lag behind peak solar heating by hours or days. Two comets can have the same overall brightness and still produce different thrust because their vent geometry differs. A single comet can change its thrust direction over time as it spins and as seasonal illumination changes across its surface. So if you're looking for a simple explanation, one calls one line, one tidy answer, the comet refuses. Not because it is a mystery machine, but because it is a rotating, venting, evolving body, and the force it experiences is the sum of many small physical processes. 3IATLAS also gave observers a visual clue that it is not a quiet traveller. It displayed evolving coma structure and unusual tail geometry, including a rare sun-facing anti-tail and jet features that appeared to wobble consistent with rotation. In studies reported during its inbound phase, those jets were interpreted as evidence of outgassing behaviour, again the ordinary engine of comet activity, but in an object that formed around another star. That jet activity matters because jets are exactly the kinds of features that can produce a measurable recoil force. And then came perihelion, the moment when the comet reached its closest point to the Sun. 3IATLAS reached perihelion around late October of 2025 at about 1.4 astronomical units, roughly the distance of Mars' orbit. It was never close to Earth in the cinematic sense. In fact, it posed no threat to our planet, remaining far away during its journey through the inner solar system. But perihelion is when a comet's activity is often most intense. The Sun's heat is strongest. Sublimation peaks. Jets can strengthen. And if the outgassing is asymmetric, stronger on one side than the other, the non-gravitational acceleration can become more apparent. Around that period, observers noted that the comet brightened in ways that were not perfectly in line with the simplest expectations. Brightening is not itself a course change, but it's connected. Increased brightness often means increased outgassing and dust production. More outgassing can mean more thrust, and when you combine unexpected changes in brightness with orbital residuals that suggest non-gravitational terms, you get a story that sounds to a casual reader like the comet is doing something uncanny. But comets do this. Even familiar comets can brighten unexpectedly, fragment expose fresh ice, or shift activity patterns as they heat. A surface layer can crack, a new vent can open, dust can collapse and uncover volatile-rich pockets. A comet is not a controlled device. It is a stressed, heated, spinning object responding to sunlight for the first time in perhaps billions of years. Now here is where the phrase "no one can explain it" usually enters, and it often enters for a very specific reason, because the first models don't all agree. Some early analyses can find only upper limits on non-gravitational acceleration during certain parts of the observing arc. Later analyses, including those that incorporate data around perihelion and after, can find that the best-fitting models include measurable non-gravitational terms. Different teams can infer different nuclear sizes depending on how they interpret the acceleration and how they estimate mass loss. Some papers explore exotic volatile mixes. Other work argues that conventional outgassing, especially from carbon monoxide and carbon dioxide, can reproduce the acceleration without needing anything strange. And if you read headlines rather than the actual logic of the work, this normal scientific spread can look like confusion. But it's not confusion, it's refinement. Science often begins with a mismatch, then expands the model until the mismatch disappears. For comets expand, the model often means adding realistic non-gravitational forces and improving estimates of how gas emission changes with distance from the Sun rotation and thermal lag. Once you do that, the course change stops being a dramatic anomaly and becomes what it truly is: the recoil of sunlight-driven jets. The remaining uncertainties are not about whether physics exists. They're about which exact physical parameters dominate how collimated the jets are, what fraction of the surface is active, how deeply volatiles are buried, and how the spin state changes. These are hard to know because the nucleus is tiny far away and mostly hidden inside a coma. And that leads us to a beautiful, quiet irony. The more alive a comet looks, jets tails, outbursts, the harder it can be to model, precisely because the activity that makes it visible also makes its motion slightly less simple. Now let's address the other half of the title, just change course. The word just suggests something sudden, something happening now. But most reports of 3IATLAS changing course refer to course differences identified after improved orbit fits, often around periods when activity rose. In other words, the changes discovered in analysis not witnessed as a sharp event. You don't look through a telescope and watch it turn. You look at the data and realize that gravity-only motion doesn't perfectly match, and then you test non-gravitational models and watch the fit improve. So if you want to picture what happened in the simplest, calmest way, imagine this. 3IATLAS is rotating, one side receives more sunlight, that side vents more strongly, the gas leaves at high speed carrying momentum away, the comet recoils. Over days and weeks, those tiny recoils add up to a measurable change in where the comet appears relative to where a purely gravitational orbit would place it. That is the course change. It is not a decision. It is momentum conservation in action. Now, because this is an interstellar comet, there is an extra layer that makes the outgassing potentially more interesting than usual. An object formed around another star may have different volatile ratios than typical solar system comets. It may be richer in certain ices that sublimate at larger distances. It may have a surface crust that behaves differently. Its internal structure could be more or less porous. Its history, cosmic rays, long, cold storage, past stellar encounters could have altered its outer layers. So when it vents, it may vent in patterns we haven't seen much before. But again, no one can explain it. We are learning what another planetary system's comet looks like under our sun. And 3IATLAS gave more than orbital hints. It also gave time markers that help ground the story. It came no closer than about 1.8 astronomical units from Earth, roughly 270 million kilometers. That is far. It means Earth was never in danger. The drama here is not proximity, it is interpretation. The comet came close enough to study, not close enough to threaten. After perihelion, the comet moved outward again on its escape trajectory. Observations continued when it re-emerged from the sun's glare, and people even followed it with public telescope live streams as it headed for the outer solar system, because an interstellar visitor is rare enough to deserve a goodbye. And while it left, the analysis continued. That is often the real timeline of space mysteries. The object is seen then gone, and only afterward do we fully understand what it meant. The data becomes a slow conversation among observers, modelers, and theorists. The orbit is refined. The non-gravitational parameters are estimated. Size ranges are debated. Coma composition is inferred. Rotation periods are tightened. And the initial "it shouldn't do that" gradually becomes "it does that because..." Now let's slow down and look at why comets are especially good at producing the illusion of intentional motion. A rocky asteroid, even a strange one, is mostly ballistic. Gravity dominates. But a comet is a leaky container of volatiles. It is more like a dirty snowball with vents than a rigid rock, and vents create directionality. If outgassing were perfectly uniform across the surface, the forces would cancel out. You would get mass loss but little net thrust. But cometary activity is rarely uniform. It concentrates in patches, in cliffs, in pits, in areas where sunlight reaches more directly, in regions where the crust is thinner, or where a recent outburst exposed fresh ice. When those patches vent, the thrust becomes directional. Now add rotation, and the thrust direction changes throughout the day of the comet. Add thermal inertia, and the strongest outgassing might lag behind local noon, producing a time-shifted thrust pattern. Add topography, and jets can become collimated like narrow hoses rather than diffuse evaporation. In that environment, a course change is not surprising, it is expected. And the best part is that you can connect the orbit drift to visible behavior. Jets and anti-tails are not merely pretty, they are evidence that material is leaving the nucleus, and material leaving the nucleus is the physical basis for non-gravitational acceleration. So the orbit and the image are telling the same story in two languages, one in astrometry, one in dust. Now, because this topic tends to attract sensational claims, we should gently place one boundary. Some public figures and tabloids have suggested that non-gravitational acceleration in interstellar objects could indicate artificial propulsion. That speculation became famous with earlier interstellar visitors, especially when acceleration was measured without clear cometary activity. But 3IATLAS is different in a crucial way. It shows obvious cometary behaviour. Coma tails jets, meaning there is a natural mechanism available that fits the observation. And when there is a natural mechanism that fits the scientific default, is to pursue it thoroughly before entertaining extraordinary alternatives. This does not mean the comet is boring. It means the comet is real, physical and rich. Interstellar comets are time capsules of other systems. Their volatiles may be different. Their dust may be different. Their activity may reveal how common certain ices are in the galaxy. Their very existence tells us about how planet formation ejects material into interstellar space. Their orbits hint at where in the galaxy they may have formed. Even their jets can teach us how sunlight interacts with foreign ice mixtures. So the better story is not no one can explain it. The better story is we can explain the basic force, and now we're learning the details. And those details matter because they shape how we predict the comet's future path. If you want to point a telescope at it on a certain night, you need accurate ephemerides, accurate predictions of where it will be. If non-gravitational acceleration is significant, predictions must include it. That's not just academic. It is the difference between finding the comet easily and missing it in a crowded star field. It also matters because interstellar objects are rare and each one is a precious dataset. We may only see a handful per decade with current survey capabilities, and each arrives on its own schedule from its own origin, with its own composition. When one shows strong activity, we learn about interstellar chemistry. When one shows unusual acceleration, we learn about how common outgassing-driven thrust is in foreign comets. When one brightens unexpectedly, we learn about how volatile layers respond to heating after long interstellar dormancy. Now imagine what it means to be 3IATLAS entering our solar system from deep space. For perhaps millions or billions of years, it drifted between stars at a few kilometers per second relative to its local neighborhood, or perhaps faster. In that darkness, its surface was bombarded by cosmic rays. Its volatiles were preserved. Its dust slowly changed. Then at some point it fell into the sun's gravitational influence and began accelerating inward. The sun grew from a bright star to a blazing furnace in its sky. Heating began. The first wisps of gas emerged, then more. The comet's surface began to evolve rapidly compared to its long interstellar calm. Jets formed. The nucleus rotated. Sunlight struck different regions. Activity surged, faded, surged again. Dust lifted off. A coma formed. A tail formed. A rare anti-tail appeared. In the orbit fit a small non-gravitational push appeared. To us it looks like a mysterious swerve. To the comet it is simply what happens when a frozen body meets heat and starts to leak. And after that brief inner system passage it leaves again, carrying the memory of our sun's heating in its altered surface. It continues on a hyperbolic path into the outer darkness, past planets it never approached closely enough to be captured by, into a journey that will outlast every civilization currently alive. Its course change, if it had one, is now baked into its outbound trajectory, a tiny imprint of sunlight and venting recorded in its final direction. Now, if you want the most honest answer to the title, did it change course and can no one explain it? The answer is this. Yes. 3. IATLAS shows evidence consistent with small deviations from a purely gravitational orbit, the kind of deviations comet scientists describe as non-gravitational acceleration. And no, it is not true that no one can explain it. The leading explanation is anisotropic outgassing jets of gas and dust that act like tiny thrusters. What remains under investigation is not whether jets can do it, but exactly how strong the jets are, what they are made of, how the thrust lags behind heating, and what that implies about the comet's size, mass loss rate, and surface structure. And that is a far better kind of mystery, not the mystery of a hidden hand, but the mystery of a natural object from another star revealing its physics to us in real time, one small deviation at a time. So the next time you see the phrase change course, you can translate it into a calmer sentence. You can hear it as the orbit fit improved when we included outgassing-driven forces. You can picture a rotating nucleus with a few active vents. You can imagine a faint, steady push from escaping gas. You can imagine the orbit drifting by tiny amounts detectable only through careful measurement. And you can let the drama soften into something steadier, a reminder that the solar system is not empty, not static, and not isolated from the galaxy. Sometimes something from another star passes through our neighborhood. Sometimes it behaves like a comet. Sometimes its jets wobble. Sometimes its brightness surprises us. Sometimes its orbit needs extra terms. And none of that requires panic or engines or impossible explanations. It requires patience telescopes and the willingness to accept that gravity plus venting can create behavior that from a distance looks almost intentional. 3IATLAS did not need a plan to change course. It only needed sunlight.